So, like we saw last time, and to the people that also did not see it, we have this little game where one can like draw this like procedurally generated world, and we can see it's procedurally generated because different ores show up. There's like something that looks like water or nectar or whatever, and some ore here, and like it looks a little different. Some mined out stuff here, and we can also see that we can change to all the different materials, and they kind of merge together. The glitches that you see is just me drawing very badly. It's not actually to do with the programming, which is the point of the show. So it's fine. um, yes. So the way that this is offered, oh my god, my cat is annoying me again, is not related to the canvas, but it is related to the marching square grid offering. So we have this game object, and on it we store something called sets. And what a set is just a marching square set. Because the thing to understand about the marching square algorithm, and this is obviously not related to ECS, but I do need something to show as an example, so I'm going to have to explain marching squares for you guys. Is you have this grid of nodes that determine the material. Right now, what you're seeing is not a debug display of the material values. Obviously, you can see it doesn't change the material values here, but it is a fact of if we look at a square, and what makes up a square is this here, like this makes up a square. So the material of this little node here is going to be of one of ore, like a iron ore in case. And then if we look here, these are all going to be stone, like filled in stone, these 3 nodes here.
So do those nodes represent kind of the edges, like the corners basically of a node or square?
Yeah. They exactly. They represent the corners of a tile that is like one of 16 different options. Because obviously, if you take these 4 states here and say whether or not there is a value, you're going to end up with 16 combinations of on and off, because there are 4 corners, and therefore you need 16 combinations of textures, where if all of them are 0, you draw nothing, and if all of them are 1, which is a value of 15, you will draw a filled-in section. In this case, for if the 4 nodes I'm selecting now, you can see I'm drawing half filled-in section, because these 2 are going to be 0, 0, and 1, 1. And therefore, I picked the tile where it's filled in on one half and not on the other half. And for the iron ore, I'm going to have to inverse that. So the iron ore itself is only going to draw where it has a filled-in section here, but a non-filled-in section over here, if that makes sense.
Yep.
And that's kind of what this is about. If you notice, there are 3 sets in here, and this is sort of the raw data representation of our problem area. Is we have 3 ores, and I guess a 0 ore, but that's just the non-existence of any material being there. If we look, there's a tile set now of 16 different combinations, which all map to a texture. So if we quickly look here, you can see this is the 0 option. This has 1 bit enabled, and 1 bit is always the bottom left corner, right? Mm-hmm. And then the next bit would be bottom right corner, and the next one would be 3, where both these bits are on, so therefore it's the bottom is enabled. Then it's going to be the next one, then the first corner again, then that corner, and then where 3 of them are enabled. You can sort of see how this texture is set up in a way where
exactly.
It's representing the bits, and obviously the last one is going to be totally filled in, and then you have a similar scenario but for the ores.
Next one, yeah.
Yeah, and water as well. The water looks so cool to me.
I was gonna say, I think, yeah, when you kind of scrolled past the whole section of water, like it looked cool, like everything was kind of flowing together, like all the lines lined up and everything on the different tiles.
Yeah, it was very hard to make. I will say.
I'm
Anyways,
sure.
um, yeah. So that's kind of our like raw ore set, so to say. That's why they're called set. They're it's a marching square set. I call them. Also, my mouse is flipping out right now. Um, then we have something called the sprite target prefab, and we have a grid lock prefab. Um, and I don't even remember what these are, but I will quickly see. They seem important. Um, Actually, I don't think they are. So let's just ignore them for now until we see them pop up in code. Yeah, and there's not anything else we actually need from an offering point of view, because the next element is just making sure that we, in this grid, that we can see selected now. And this, by the way, is very, very satisfying. Notice that I can click in the editor and we're not in play mode and everything is showing. Which means that we now sort of have a like pre-rendered view of what our generated scene is going to look like. And that's going to be some of the code I'm going to show soon. We can kind of see it's split into these 3 layers. There's like one here, one there, and I don't even know if the third one is that a third one or is it the second one? I think it's just the second one.
Hard to tell.
Not behind it. Because here the thing is, obviously 3 separate textures can make it at the same time. Like you could have a third corner here that is water, and therefore I would need to draw 3 at the same time. Fourth one could technically happen, I suppose. I don't know what's going to happen at that point. Oh yeah, there are only 3 materials, so that could never happen. And my cat just pressed me into this. That's kind of funny. Yeah, you can see here it's because a tile has a carver and has 2 different materials on it that can go behind it. A carver is just the stone layer. There always needs to be a stone layer. That's just how I built it. There's no real reason for it. Now, okay, so now we have the data part of it. Obviously, you can already see what the output part of it is going to be. Now let's see the system part of it. Oh, well, I guess I will quickly show the baker for it. Because if we look at that asset that I was quickly looking at, and I guess the sprite target prefab, I now know what is. Sprite target prefab is for every single tile, I'm just spawning this prefab, and then I can, from that, say, well, this here is the carver, so it has tag type carver, and this here is the material A tile, and this here is the material B tile. And the reason I'm doing this is because then I can have a baker, and on that baker, I bake everything that is a marching square tile layer offer, which these are marching square tile layer offers, and say, hey, well, you are a carver. In that case, I'm going to add the marching square tile carver tag. So that means that any of these tiles, particularly this tile here, will end up being something that has a renderable, so therefore it has a local to world. It has a material override corner strength. I used this originally. I technically don't need it anymore. A material override offset XY and scale ZW. And this is relevant because the way sprites work, I will show in a second. Where I offer in the textile size, etc. Again, I will show this in a second. And then at the very least, as I said earlier, we have a tag type. If it is a carver, we add the carver tag. So that we can query for, we can initially spawn out all the tiles just up front, and then I can just do a query saying, hey, loop over all carver tiles. Hey, loop over all of the material A tiles, all the material B tiles. This is a case where it does actually make sense to have different arch types for the 3, because it means we can query quickly for 3 different layers. Yeah. Now I'm going to quickly show what this material override offset XY scale is. And it kind of has to do with the fact that, look at these wacky things that almost look like legs. They are, in fact, an artifact of them being a sprite from a sprite sheet. because entities does not support sprites. They do, however, support normal mesh drawing, so you can draw a quad totally fine.
Right.
And that quad can have a material on it, and therefore it can have a custom shader on it. So I have written a custom shader graph, which is a fairly simple shader graph. So I guess there is actually going to be some shader explanation in this tutorial, but it's not a very advanced one. Um, yeah, this is the entire shader. And what it essentially does is we have this texture here, which is our main texture, which is the sprite sheet that contains all tiles in the whole game and all other assets. And it's split up into like specific small sections where the actual like given tile that we want is going to be, and therefore we need to change both the scale and the offset. So we change the scale at the start because the scale of the texture is not going to end up changing later on. So therefore, the scale is just going to be, the size of a tile. So we end up, we know the full length of the whole sprite sheet, and then we just divide it up into like a 60. I think we divided by 16 minus some amount or something. We saw that in code earlier. That is what we're doing here. I guess we're saying sprite sheet textile size times 32, which will end up giving us 32 pixels, I suppose. Yeah. And then we also, we don't see it here that we bake in the offset because where we actually bake in the offset is out here. Because when we saw earlier, this is actually where we defined the sprite. No, not the canvas, but the marching square one. The sets here. Boom, boom. This is what actually defined, like a sprite is defined by the offset. So I can simply now that I have the correct size, I just need to set the offset. So every frame to set up my grid, I now just change the offset, which is very nice. And technically you could change instead of changing an offset, you could also change the material mesh info, which would therefore change a 3D model instead. So you could do this with the 3D model fairly easily if you just use a render mesh array. And we might have a tutorial in the future about that, because I'm very curious about trying to do that. I think I kind of mentioned that in a previous video where I was like, wouldn't it be fun if Voxel, we did a Voxel editor?
Yeah.
So, anyways, I think that was the last episode. If we look, is this a cave grid offer? Marching square, I suppose it is. Yeah, here we can see that cave grid offer. This is the thing that we were looking at earlier. This one is a array of sets, and every set is made up of 16 sprites, and 16 sprites then end up in here. So for every single set, we add a buffer of matching square set, and every match square set is an element in that buffer that contains all the 16 different offsets, if that sort of makes sense. You can also see I have added comments here saying, well, this is the left bottom corner, this is the right bottom, this is just the bottom, this is the right top, this is the left bottom and the right top, this is the etc. So you can kind of see all the different combinations, and we just store that inside one buffer element because I need those. I need these offsets anyways, so it's not going to cost me that much to just contain it all inside one structure. It would actually add more overhead if I had, like, I don't know, one big buffer and I had to divide it by 16. It would also make it harder to think about the problem. So by sort of doing this manually, it certainly makes the code a lot easier to read. The only other thing I'm doing here is making sure that our big offering element that knows all and tells all not only knows about the matching square sets that exist, but also it is not going to be a movable entity itself because it's just some offering data that we need. It also has the tile prefabs so that we can spawn a bunch of tiles, And the gridlock prefab is the, remember when I showed all the little grid cells? That's what this is going to help me spawn. I only use those for debugging. They're not actually part of the game itself. Yeah, so that's all of the offering part of this. Obviously, we're soon going to get to the point where we can see why it also works in the editor. But for now, the important part of offering for something you want to be ready for the editor is just to make sure that you have a database setup. Like the one of the problems that can often arise if you're trying to write something that also works in the editor is you can't have something that is dynamically changing. Um, it like you don't want a native array dynamically sort of like I press a button and then it has like a static that you add to. There's some weird cases, specific cases that you can get into. You sort of need to make sure that you just have, this is the data, and from that piece of data that I have, and that it's not changing, sort of like a declarative language like CSS and HTML. It's just there. It knows that it can read from it, and then the product of your algorithm, procedural algorithm, in this case, matching squares, will just produce it live dynamically. And that's the part that can be dynamic, which does mean it has to be able to reproduce this fairly fast, because obviously otherwise it's going to end up lacking your editor, or either fast or asynchronously, right? Which there are other ways of doing. Now I think we're going to go into the actual system, which is called the matching square system. I just need to find it. Uh, damage system, construction system, Cape grid system, I think it is. Yes, correct. Holy shit, there's a lot of stuff in here. We just want the important bits, which is the cave system. Cave grid system, yes. So I'm updating after the transform system group. And this is because before the transform system group is when all of the local transforms can be updated. Afterwards is when you can modify any local to worlds. So if you just want to modify the local to world directly, you need to do it after the transform system group. And there's some code that's going to be in here that's going to change the local to world. Okay, so there's a bit of utility functions in here, but those we'll get into later when we actually go to read the code. So on startup, what I want to have happen, and just for now, think of this like a normal system. Do note that this system is actually also run in the editor, but it's also run in play mode like normal. So we had that grid system that we had earlier, that offering element, and as soon as we enter play mode, that's when we're actually going to generate the procedural map. Similar to how when you play Minecraft or something else, you only want to generate it when you actually hit create new world or something. So this generation step does actually happen in play mode, because that's where you want it to be, because you want the user to be able to type in a dynamic seed or something. So okay, we add a new singleton, and this singleton is actually what stores our cave grid. Our cave is made up of a grid list and a tile list. And what these two types are is basically just a wrapper saying, hey, this tile list contains every single tile in there. And the grid list is going to contain every single grid node. So our grid node is what actually contains our data. That's the four corners that we were talking about earlier. Is all contained inside one contiguous native array. And to get the width, well, in this case, I've chosen a constant width. So it means that there are going to be 20 grid points from one end to the next end. And we can actually see that when I went into play mode here. I'm going to try to do it slow, because I know encryption and I know the compression can get bad if I move too much. But if we look here and I go into grid mode, you can see that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I must have miscounted one there, but that should be 20 from end to end here. And you can see it skips over every other one because that doesn't count. So that's what this array is. It's going to be a width of 20, and then it's going to be height by the grid length divided by the width. And the grid, this also means that naturally what happens is if I were to expand the array here, it will just naturally grow downwards. It means you can have an ever expanding downward cave. And you could do a similar thing in Minecraft, by the way, when you have a 3D voxel grid where you can make sure that it grows in specific directions. Which is very nice. Okay, so let's go down again. It does get a little complicated. But yeah, that's why we are allocating the grid. We're allocating it as a size of the width and the default initial row count, which is 128. So it's 128 rows down of grid nodes, which also means that because it's 20 grid cells wide, it's going to be half of that amount of tiles in it. No, not even half. It's good. I guess it's going to be like -1. Yeah, because it's like obviously a tile needs 2 cells, but then the next tile will reuse the previous one. And that keeps going until the end where it will have reused the previous one, but then it still needs the new one, so it's going to be 19. It's kind of hard to visualize, but I hope that made sense. Yeah, okay, so we add this singleton to our system. We say that the grid length is equal to the width times the singleton row, and then we resize the tile amount. This is kind of boring, but anyways, what ends up happening here is that what we want to do initially when we have our onCreate is that when the system spawns, we've set up an array that contains our entire grid, and in that grid, it has done the procedural algorithm. This could also just as well have been inside of you hit a button and only then does this an on start running. So when you press a button, an entity spawns, and then on start running starts calling all of this initialization, setting up where the ore is going to be, what water is going to be, where the ore is going to be, where the air is going to be, how you mix all of these together. Like you can see in here, there's this sort of hole made, and the way that hole is works is that it checks, hey, if the y is 0 or 1. So 0 or 1, 0 is up here, 1 is here, and it is 6 or 7, 6, 7, then you should pick air. Otherwise, you should pick rock. Oops. And then that's what we assign to the grid cell. So that means now this is going to properly fill out this entire grid with all the materials of that grid. And we have a nice little native array that has everything we need. In on this thread, we obviously dispose the data. I don't think we need to go into detail on that. On start running, make sure that we spawn the prefab tiles at this point. The reason we can't do this in onCreate is that, like with any sort of offering dependency, we need to wait for that scene to have loaded. onCreate might run before a subscene has loaded, and so therefore we need to wait for that subscene to have loaded, and therefore we do it in on start running. This is also where we say state required for update March square data, and the March square data was this data over here. So we're waiting on that data to exist so that we can spawn a bunch of tiles, because as you can also see here, all the tiles are known from that March square data. Yeah, and then we get from the singleton is where we get the cave grid height, and then we just loop. So for all of the width, -1, as I said earlier, we spawn a tile and we set the position of that tile through the local transform. It's kind of ironic in a way that I'm setting it through the local transform here because I am saying update after. But it does mean that what's it called? It will cause a 1-frame delay, but since the offset also matters and the first offset in the sprite grid is invisible, then it's actually not going to show any problem. Another way of solving this is just to have this specific part in another system, because the actual on update is what needs the changing of the local to world. But yeah, okay. So every single frame, and this is a frame in the game. We're not yet at the point where we are going to say anything about the editor. Every single frame, we want to make sure that if you had updated the grid, and there's some optimization you can do here, like don't do it every single frame, do it every single frame where someone has made a change to the grid. Then you should update the 3 tiles. Again, we remember we had the carver, the material A, and the material B. And so first we update the outline. I don't know why I call it the outline tile, because it is clearly the carver tile, which I wrote in caps. But you can see here, I'm saying, hey, for every single local to world that has a material override offset XY and a carver, and that is a carver, please let me change some values on that. What values am I going to change? I'm going to change the offset on it so that I can make sure that this specific tile is going to draw the correct tile. And the way that it knows the correct tile in this case is from its input. What was the input? Well, the input was the native array that we just created earlier with all the correct ors in it. So if we look here, corners equals 1 minus int 4 saturated. Well, what that means is that we sort of want the inverse, and that just has to do with how the texture is set up, is this here is what samples the 4 corners, right? So it takes the local to world. It has this little utility function. It's just a static function that returns, you can see here, it returns an int2 for the grid array. It's just a typed version. It is literally just an int2 that it returns. It just makes sure that it converts it correctly. Because one of the annoying things when you have arrays like these is it can often get very, very hard to figure out, oh, do I currently have an int2 that is pointing to the tile or an int2 that is pointing to the float to the what's it called, like the grid cell, because they are offset. Like the tile is 0.5 coordinates different than the actual like grid cell. That the two are different.
Right. The origin of your visual representation of the tile, you mean?
Yeah, exactly. So that's why there's a typed version here saying, well, this int2 is for a grid array. So local to world to a grid position, and that's get corner values. You can see that this takes in an int2 for a grid array. And that therefore makes sure that you always pass in the correct sort of coordinate to it.
That's nice.
Yeah, it's my own little custom way of doing this, but I do like it. So this gets me the 4 corner values for a given tile, because again, this is going to loop over every single tile that is spawned, every carver tile in particular, and then this here makes sure to convert it to a grid position, specifically the top left grid position, and then this samples the corners. So the top left, including +1 plus the width, so it goes down 1, and plus the width +1. Therefore, you have the 4 corners. And then that will give you a value of either 0, 1, 2, 3, or 4. And I think actually to quickly show what values it will give, I have an enum. Boom, 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 here. because that's the other part. Cave material type. So 0 is rock, 1 is air, 3 is, wait, did I say that? 2 is ore, 3 is water. Um, yeah, good. And that means that since 0 is stone, and what we can see here is that we have, okay, corners equals uh, highest corner. Oh, wait, that's later. Never mind. Yeah, here. Yeah, we have the corner, and we want to make sure to draw the one where this. I always get these two flipped. I guess we can see that by the texture. Actually, it's a little easier. Yeah, okay. 0 is the one where there's no stone in it, but since we have an enum where 1 is the value of air, therefore, if 1 is here, then we want a value of 0. If 0 is here, then we want a value of 1. Because that's how the texture is drawn,
Right.
not
You
how
just
the
gotta
enum is set up.
flip the
Yeah,
mapping.
exactly. So that's what we see here. Once that mapping has been flipped, I've flipped over all of the int4, right? All of the 4 corners values, and then I just merge them together. And that makes like our get offset from this. Because remember earlier we had an array where this is offset 0, this is offset 1, 2, 3, 4, 5, etc. We have this little nice utility that makes sure that we can use this as if it were an array. So you use this type as an array. It's kind of funny. So yeah, I pick the stone set. The stone set is the first set, so that's the 0 part here. Please, from the stone set, give me an offset of the based on the combined value of the 4 corners. And this is the X corner. This is the Y corner, which is the top, I guess the bottom right. And this is the so on, right?
Yep.
Just like we saw earlier. And this live updates those values. And then that's the stone covered. Then we just need to make sure that we also cover any other X material. So I have a high preference on the stone here just because I felt like for this sort of generation, I wanted stone to always be visible. But down here is where you can see that it will actually also work with n number of materials. And that's because, as we did before, we got the corner values like the last time around. But we remember that the corner values, and by the way, the reason that we saturate here, they can be above 1. They are a value of 0 to the size of the enum, and the enum represents the amount of types that we have. Like types of ores and types of, yeah, it's water, stone, rock here, right?
Yeah. Whatever. Tile type. Yeah.
Yeah, exactly, tile types. And then we sort the 4 numbers. That means that we now, in this container here, know that the X value is always going to be the highest value, and then the Y is going to be the next highest, and so on, right? So this just makes sure to sort those 4 numbers in the corner. Which means that we now have a stable ID of what is going to be the lowest material. And that's what I'm getting here. I'm basically just asking, hey, which of these 4 corners map to the lowest material? Then say 1 minus that, again, because I'm gonna have to convert like this. The equal sign here will give me a 0 to 1 value, right? And then I still have to do that reversion that I did on the other one as well. Again, because that's how the assets are drawn. If I had just drawn them correctly, I didn't have to do this flipping.
Hey, that's game development. Sometimes you got to do that, right? Do those little hacks to work with whatever assets you got.
Yeah, exactly. Um, but yeah, no. So here, what I'm just doing is I'm saying in the marching square set, please pick out the clamp. So pick between the highest value with the low. Yeah, this is going to be the one I'm currently trying to draw. And this is going to be lower bound and upper bound so that I don't try to pick something that is outside the size of the marching square set. And then, like before, I'm doing get offset, and then I'm setting that as the offset inside of my material offset, which is here. And then I'm doing the same thing again for the next one. There's a complicated here because I need the second highest corner. And there's like some cases where, okay, if W does not equal the set corner, then that's the set corner that is valid. If it's otherwise, it might be the Y corner that is the second highest. Otherwise, it might be that it is the X corner that is the highest valid second. And then I can do a mapping again. Boom, boom. And this corner strength here just makes sure that I can either I draw that tile or I don't draw it. I don't want to draw something that doesn't have a valid second. And that's sort of it for how I'm updating the tiles. The only specific thing, and notice how all of this is like, I am spawning and instantiating a set of tiles. I am updating those tiles to the correct values. But because all of this is based on data and that this is run as soon as I enter play mode, it's actually gonna be totally fine if this was also an edit mode system, because the difference between the two is that an edit mode system, you can sort of think of them as doing the same step just when you exit play mode. So when you exit play mode, it will run create of an edit mode system. So therefore, it will make sure that we, have
Right.
set up a
Your
native array.
initialization logic all starts and everything.
Exactly, and it will properly instantiate as well as soon as I exit play mode, and then it will again update all the values correctly. And so if we look up here, I had, and this is I don't mean this lightly. I had written this out during like one day, and then I went at the end of the day. Wait a fucking moment! Wouldn't it work to just put this attribute up top? So I did. I just like put this right here. Because we were doing like a hack week. This was initially made for a hack
Oh
week.
yeah, okay.
So I was kind of on a time limit on getting everything to work as quickly as possible. But yeah, this just worked out of the box, typing in editor, and that was because the initialization and on create is already written in this way where everything is just spawned as soon as you exit play mode. And that means that this system both works in play mode and in edit mode. I didn't have to write two different generation systems. And that's sort of it.
Now, do you have to do any sort of cleanup at all? Like when you enter play mode, do you have to like delete any of the editor entities so that the play mode entities can now spawn, or does that all just kind of?
That all sort of works because as soon as when I press play here, what actually ends up happening is I'm gonna call dispose on my editor
Oh, right.
world.
The editor world just gets completely destroyed. Of course, yeah.
Exactly, the editor world that gets disposed, and then the play mode world gets entered and therefore
Right.
created, and vice versa. As soon as I exit play mode, it's my play mode world that gets destroyed, and then
Right.
it just enters the edit world. Yeah, no, it's fairly easy. So as long as you've made sure that your on destroy also destroys things properly, it's gonna be very nice to write this.